My name is Jared Jacobs. I'm a student at Lake Wilmerding High School in San Francisco, where I study architecture. I'm also a volunteer for the Stanford Building Decarbonization Learning Accelerator. Today, I'm going to show you some of the architectural elements that help make a decarbonized building. Did you know that 40% of global carbon emissions come from building construction and operations? That means that buildings are a huge negative contributor to climate change. But that also means that architecture represents a great opportunity for us to have a positive climate impact if we develop decarbonized buildings. Building decarb involves the design of new buildings and the retrofitting of existing buildings so that they contribute zero or near zero carbon emissions. Building decarb relies heavily on energy efficiency and is focused on eliminating the use of fossil fuels in buildings through building electrification and the use of renewable power. Building decarb also reduces embodied carbon by minimizing greenhouse gas emissions associated with construction materials. Rapidly reducing greenhouse gas emissions from buildings is critical to addressing climate change. The Stanford Building Decarbonization Learning Accelerator, BDLA, is a nonprofit organization that helps future architects, engineers, and construction managers learn about building decarb. Teachers can access free case studies, slide decks, videos, and other resources on the BDLA website to use in their existing classes. The BDLA also hosts virtual workshops and collaborates with colleges and universities on a wide variety of building-related topics. Typical buildings aren't designed to be super energy efficient. Plus, they're powered by a combination of fossil fuels and electricity generated from non-renewable sources. There are several steps along the design path to creating a decarbonized building. The first and most critical step is to make the building as energy efficient as possible. The next step is to make the building all electric. And finally, all the building's electricity needs to be renewably generated. We're talking about solar, wind, geothermal, and other renewable energy sources, all with battery storage. No fossil fuels allowed. In this video, I'm going to focus on the architectural design strategies that make buildings as energy efficient as possible. The first strategy is building orientation and massing. Building orientation refers to the position of the building on the site. Massing refers to the shape of the building. In general, a longer, narrower building with shorter east and west facades is preferable. Here's the reason why. The sun rises in the east and sets in the west. Sunrise and sunset are when the most direct solar radiation hits the building. We want to minimize the amount of direct solar radiation that hits the building in order to reduce the amount of heating and cooling needed to keep the building comfortable. The next strategy is high-performance glazing. Lots of existing buildings have single or double-paned windows with metal frames that allow unwanted heat to pass in and out of the building. Instead, we should use double or triple-pane windows that have a low E coating and a thermally broken frame. This helps prevent unwanted heat from passing in and out of the building. Another type of high-performance glazing is called electrochromic glass. It changes its tint throughout the day depending on the amount of sunlight hitting the window. Electrochromic glass allows the building to dynamically block solar radiation during peak hours to prevent excess heat from entering the building. This reduces the need for additional cooling. Another strategy is creating a lower window-to-wall ratio. Current design trends lean towards buildings with larger windows and exterior walls that are sometimes made up entirely of glass. This allows unwanted heat to easily pass in and out of the building, making the building very inefficient. Ideally, we want to design buildings with a 40% or less window-to-wall ratio. Now let's talk about using different window sizes depending on building orientation. We can use larger, well-shaded windows on the south facade of the building. During the summer, south-facing windows reduce the amount of unwanted peak hour solar heat gain since the sun travels along a path that is higher in the sky. During the winter, south-facing windows allow for more intentional solar heat gain as the sun travels along a path that is lower in the sky. On the east and west facades of the building, we should install smaller windows since sunrise and sunset are when the most direct solar radiation hits the building. Another strategy we can use is improved daylighting and views. Most offices have large floor plates and low ceilings, so very little daylight penetrates into the middle of the building. Access to daylight improves occupant health and well-being while also improving energy efficiency since electric lighting can be dimmed or even turned off if there is enough daylight. The building on the right shows a Google office in Mountain View that is completely illuminated but with very little electric lighting. Light shelves can also be used to increase daylight penetration. Daylight bounces off the shelves so that it can get deeper into the space. Next, let's talk about exterior shading. It's very common for buildings to be entirely covered in glass without any shading. If a building has large windows, the best way to minimize the energy impact is to add exterior shades. Interior shades block glare but still allow solar heat to enter the building. Exterior shades are much more useful than interior shades because they block solar radiation before it enters the building. Fixed shades don't move, and they block sunlight in the same way at all times of the day. Operable shades are very useful because they can respond to outdoor conditions in real time. Next up, we've got increased building insulation. Typically, buildings have lower quality insulation that is only installed between wall studs. The studs can act as thermal bridges, allowing heat to easily pass through the wall in certain areas, completely bypassing the insulation. Ideally, we want to install lots of high-quality insulation between the studs while also adding continuous insulation over the entire wall to eliminate thermal bridges. Most existing buildings don't have insulation under their slabs. This makes the slab a thermal bridge. Including an insulated slab under the ground floor helps reduce unwanted heat transfer. Next, let's take a look at creating a tight building envelope. Outdoor air can enter a building through small cracks and gaps. This unwanted outdoor air needs to be offset with additional heating and cooling. Better sealing reduces unwanted infiltration, which means less heating and cooling is needed. Now let's talk about thermal mass. Thermal mass is the ability of a building material to absorb, store, and release heat. On summer days, cool concrete absorbs heat that comes through the building envelope. On cool summer nights, that heat can be flushed out of the operable windows, the concrete is recooled, and the cycle repeats. This process is called a nighttime purge. During the winter, a similar process occurs, except for that at night, the heat is released into the building instead of being purged. Concrete can act as a thermal mass, absorbing heat during the day and releasing it at night. Thermal mass helps maintain a more constant space temperature without using any additional energy. This allows us to install smaller heating and cooling equipment. Even buildings made of concrete are often covered by carpets, wall finishes, and drop ceilings, which blocks the thermal mass. Leaving concrete exposed can make the building more energy efficient. We also need to leave sufficient space for building systems. Long straight air duct runs without a lot of twists and turns use less energy since it's easier for a fan to blow air through the system. Be sure to keep roofs as unobstructed as possible so that we can maximize the number of solar panels. We should design solar-ready roof structures even if the panels won't be installed on day one. Be sure to work with mechanical engineers early on in the design process to ensure that there's enough outdoor space for things like large battery systems and heat pumps. And last but definitely not least, we have integrated design. In a typical project, the owner hires an architect who completes most of the architectural design before bringing on engineers and contractors. In this case, the design is completed in silos and there's little opportunity for collaboration between disciplines. Integrated design is a process where all designers and experts are included early on in the project and they have an opportunity to collaborate. Integrated design is the best way to achieve energy efficiency goals because it helps ensure that all building systems work well together. All of the architectural strategies we talked about in this video are critical to achieving energy efficient buildings and putting our projects on the path to operational decarbonization. If you want to learn more about building decarb, check out the rest of the BDLA website where you can access free case studies, slide decks, as well as other videos and resources. Thank you.